Okay, so far in this course, we've been looking at solving triangles, right triangles. Now we're going to get into looking at triangles that are not right triangles. And so there are law of sines, and this will help us, and law of cosines that will help us find sides or angles of a triangle that are not right. I am just going to give you the formula for the law of sines. And I'll tell you when you can use this equation. Okay, so law of sine says that if you take side A all over sine of the angle A, this is the exact same thing as the ratio of any side across from sine of that angle, across from that side. So that's the same thing as side B over sine of angle B, which is the same thing as side C all over sine of angle C. So really, depending on which information we're trying to solve for, if we're trying to solve for a side, I would usually write my fractions like this. If I'm trying to solve for an angle, it's equivalent to say this is the same thing as looking at the reciprocals. The reciprocals are equivalent. So that would say then that sine A all over side A is the same thing as sine B all over side B, or sine C all over side C. Okay, so when to use law of sines? We can use law of sines if we know an angle and a side directly across from that angle. Sometimes you don't know an angle and a side right across, but you might know two angles in a triangle, and you can find that third angle by knowing that the sum of the angles in a triangle is 180 degrees. So we can use law of sines when we know an angle and a side across from that angle. And we're going to use this for non-right triangles. If we had a right triangle, then we don't want to do this. Okay. So there's three possibilities that can occur given information about a triangle. One, there could be no triangle exists without information. One triangle can exist without information, or actually two triangles can exist without information. I always assume two triangles exist, and while I'm working out and trying to find that information for those two triangles, if it doesn't, two triangles don't exist, I'm going to get some contradiction. If no triangle exists, I'm going to get contradictions, and I'll know right away that there's not a triangle. Your book does it a little differently, and you have to memorize certain cases, but if you just kind of go in and always assume there's two, and then it will disprove if there's not two. Okay, so there's three possibilities, three possible cases. When given information about a triangle, there's either one triangle, two triangles.
Excuse me, Professor?
Uh-huh.
I think you could scroll up a little bit. I'm just going to take a picture of the notes.
Yeah, no problem.
What section is this right now?
This is 9.2. law of sines.
Okay,
So
thank you so much.
no worries. So we have a non-right triangle. If we know a side and an angle across, we can use this law of sines. If we're given information, there's three possible things that can happen when we're using the law of sines. There's either one triangle that exists, two triangles exist, or no triangle exists. And always start out assuming there are two triangles. Okay, so let's look at an example. And so let's say that you're given the following. You're given that your angle A is equal to 50 degrees. You're given that your angle C, this is equal to 20 degrees. And you're given that your side A is equal to 3. And it wants us to solve each triangle. Or solve the triangle in this case. Okay, so looking at this, I would know that I would want to use the law of sines. Just because looking at this, I see I have angle A and I have side A. There's cases that we'll learn where we can't use the law of sines right away, and we'll have to use law of cosines, but you gotta wait for that. So notice right now, we have angle A and angle C. If we have two angles of a triangle, then we know what the third angle is. So we know that they have to sum to 180 degrees. So we know that B is equal to 180 degrees minus A, 50 degrees minus 20 degrees. So that's what, 130, 110 degrees. So now all we have left to find is side B and side C. Always tend to use the ones that you're given the information, just so that if you did some arithmetic wrong, it's not affecting it. So because I'm trying to find a side, let's put the side in the numerator. And so let's look for first side C. So side C all over sine of the angle C, which is 20 degrees. This is equal to, let's use what we know about the side and the angle, which is A. So side A, which is 3, all over sine of 50 degrees. So to get the side by itself, C, all we have to do is multiply both sides of our equation by sine of 20. And that would clear our fraction, and that would leave us what C is. C is going to equal 3 sine of 20 all over sine of 50 degrees. Okay, so you definitely need a calculator for this section or chapter. So make sure you're in degrees instead of radians when you plug this in the calculator. You're going to do 3 sine of 20. Make sure you close off that parentheses for your angle, and then divide by sine of 50. And when you do that, you get approximately 1.3. So a lot of times we look at this and we look at how far to round by looking at what the information they gave us. And so I know I'm doing things in degrees because I'm given stuff in degrees. And then notice that there's no decimal places here. So I'm just going to round to the whole number when I am getting my side here. My math lab will let you know if it's something different. But so I get approximately 1.3. So rounding that, I would get approximately 1. Actually, let me, okay. So now I want to find, we're almost there. All we need to do now is find side B. So this is where I don't want to use the information I found because I really did round it a lot. Side B all over sine of angle B. Well, we found that first. That was 110 degrees is equal to, and I'm going to use the ones that were given, side A, which was 3. All over sine of 50. So just to get B by itself, we can multiply both sides by a sine of 110 degrees. So we get B is equal to 3 times sine of 110 degrees, all divided by sine of 50 degrees. So 3 sine 110, all divided by sine of 50. That gives us approximately 3.68. Or if I round to the nearest whole, 4. So given the information, we found the triangle. Okay, this is where going through this example, it reminded me, we don't always have to assume that there's 2 triangles. The only time that we have to assume there's 2 triangles if we're given a side and if we're only given one angle and the side across from it. 3 possible cases when. So this up here is when given one angle. And a side across from it. Otherwise, if we're given 2 angles, then it's only going to be one triangle that exists. Okay, so here's a case where you're only given one angle and a side across from it. So this is a case where we're going to assume that there's 2 triangles that exist. And so let's say that you are given that side B is equal to 2, side C is equal to 3, and angle B is equal to 40 degrees. So with what we're given, the only thing that we can find right now is angle C. So we can use the law of sines. We're given a side and an angle across from it. Since I'm looking for an angle, I'm going to put the sine in the numerator. So I have sine of 40 degrees all over side B, which is 2, is equal to sine of C all over the side C, which is 3. It just makes it easier if you set it up this way. So when you're solving for the variable, you don't have to do as much algebra. So isolate sine C on both sides. We're going to multiply both sides by 3. And so we get sine C then is equal to 3 times sine of 40 degrees all over 2. So we want to get rid of sine. We don't want the sine there. We just want the angle C, not sine C. And so we learned that we could take the sine inverse of both sides. And that kind of does it. So taking the sine inverse of both sides, we get sine inverse of sine C Well, that's just equal to C, equals sine inverse of 3 sine 40 degrees all over 2. Okay, so this is where we could have two possible cases of a triangle. Let's first look at this 3 sine 40 over 2.
Real quick, why did you do, why this time in this example is it sine 40 over 2 instead of the, why is it the big A over the little a now?
Okay, because this time when I was using sine of the law of sines, I was trying to find an angle. And so it's easier if you have the sine in the numerator when you're trying to find the angle. We could have put it in the denominator. It would have just given us, we would have, to isolate the C,
okay.
we had to do more math. And so that's where here when I was using the law of sines, I was trying to find the side. And so I used it where the side was in the numerator instead.
Okay.
And so here, if you plug in this into your calculator, this 3 sine of 40 degrees over 2, this is going to tell you, this is going to help us know if there is no triangle. If you get that this number is bigger than 1 or less than -1, you can't have a value that is outside of that range. Sine is always between -1 and 1. And so then no triangle would exist. When I did this and I plugged it in the calculator, I'm going to leave it like this when I take the sine inverse, but decimal form right now is approximately 0.964. And so I know that at least one angle is going to exist. And my calculator is going to give me that. This is positive. We didn't start with an equation with sine inverse in there. So there's two quadrants where sine is positive, and that could either be in quadrant 2 or quadrant 1. The calculator is only going to give me the one in quadrant 1. And so we'd also have to find the angle in quadrant 2. So this is where two triangles can exist. So triangle 1. This angle C is going to equal sine inverse of what I just had. So I'm going to just take sine inverse of my answer. I can do that in my calculator. And that spits out approximately 74.6 degrees. I'm going to round it up just because this was a whole number. So I'm going to round that up to approximately 75 degrees. Actually, I'm not going to round that up just because I know in the past, it's been so close, like a tenth of a piece away where the triangle did exist, but if you round it up, you wouldn't see that. So let's say triangle 1 is this. But this, think of this as, this was from quadrant 1, from C being in Q1, but the reference angle will give us triangle 2. So if that was the reference angle, then that would mean basically, right, you're going in here and we would have to fall in quadrant 2, and that would be our angle, which was 74.6. So like we were doing before, we would take our 180 and subtract it because it's always formed with the x-axis. And so 180 minus this that gives me about 105.4. So angle C could also be 105.4 degrees.
Where did you get the 0.964?
74, 90.6 0.0964. I got
Yeah.
that from taking 3 sine of 40 degrees and then dividing it by 2. So up here, I took this piece right in here. I put it in the calculator and got this.
Oh, okay.
So this is where, if there's not two triangles, it's going to fall out because we know that all 3 angles have to sum to 180 degrees. We have one here, 40 degrees, and we found one here, 74.6 degrees. So we can find what angle A is. So for triangle 1, A is going to be, let's do a different color. A is going to be 180 minus B, which we were given was 40 degrees, minus C, which we just found to be 74.6 when it was in quadrant 1. 180 minus 40 minus 74.6 gives us approximately 65.4 degrees.
Excuse me, Professor.
Yeah.
What do you mean when you say there's 2 triangles?
There could be 2 triangles with information given about a triangle if you're only given one angle. And so I always assume 2 exist, and if it doesn't, and we'll see if it does or not, it will just give us a false example. So for instance, right now, if I get my angle A as a negative angle, that's impossible. So I know that there's only one triangle to exist. I have to, when I take the sine inverse of something, this is telling me just the angle that was in the first quadrant. And so we also know that when we take an inverse of something, that sine is also positive in quadrant 2. And so that's where I'm using the information where that second triangle could exist. Let's see if it does. So we would have A is equal to 180 degrees. That's the last angle, we don't know. We have minus B, which we were given 40 degrees, minus 105.4 degrees. So if this is not a negative number, which I know looking at it it's not, then there means that 2 triangles exist with the information that we were given. So doing this, I get A is equal to 34.6. So I have information.
Professor, so the number we get from the inverse sign can't be negative, right?
Right. It could be negative. If it's negative, though, that's telling me that it's in the 4th quadrant, and I have to look at that. It just can't fall out of the, when you take the invert, that value inside the inverse, it can't fall outside of the range of -1 and 1. So if you got a number bigger than 1 and you take sine inverse of a number bigger than 1, your calculator is going to say error. Or if it was less than -1, it would say error. But since this was positive, I knew, that's why I wanted to figure out what this value was, so I knew what quadrant I was falling in. So we're almost there. We're given 2 sides. We found the other 2 angles. And so we just need to find that missing side A. And that missing side A depends on which triangle, which information you're using. So for side A, so this is where I'm going to put it in the numerator because now I'm looking for a side. All over sine of the angle A, 65.4, is equal to, I'm going to use the information that we were given in the original. I'm not going to use anything about C right now. Actually, I do. No, I don't have to. I know that side B is 2 all over sine of 40 degrees. And so multiply both sides by sine of 65.4. We get A is equal to 2 sine of 65.4 degrees, all divided by sine of 40 degrees. So plugging it in, sine of 65.4, divide that answer by sine of 40. You should get approximately 2.82. And I'm just going to do 2.8. So side A, if we use the angle 34.6 degrees, well, that would give me side A all over sine of 34.6 degrees is equal to, I'm going to use side B, which was 2 over sine of 40. Get A by itself, multiply both sides by sine of 34.6 degrees. So A equals 2 sine of 34.6 degrees all over sine of 40 degrees. And that should give us approximately 1.8. So the one answer they have in the book, because everything else couldn't fit and has to look in the back, is showing that they actually rounded to the nearest hundredths for their sides. So just make sure and see what they do. They didn't give me any directions on here what to round it to though. So given only one angle, a side across from that one angle, then you have to assume two triangles exist. That one will come out if it exists. If it doesn't, then you're going to be taking a sine inverse of something that's not in our domain. And it will spit out in your calculator there's some error. And then no triangle would exist. If you do get back one angle, when you do that, then you have to think about that in the other quadrant. It could have been positive or negative. And look at it that way. Let me do one more, and then we'll look at some application. So let's say A was equal to 3, B is equal to 7, and angle A is equal to 70 degrees. Okay, so again, here's a case where we're given one angle and a side across from it. So law of sines should be raising a flag saying, use me, use me. So I'm going to try to find angle B. That's the only thing I can do right now because I'm given side B. And so since I'm trying to find the angle B, I'm going to put that in the numerator. So sine of angle B all over the side, which is 7, equals sine of angle A given 70 degrees all over side A, 3. So we can get sine B by itself by multiplying both sides by 7. So we get sine B then is equal to 7 times sine of 70 degrees all over 3. But I don't want sine B, I want angle B. So take the sine inverse of both sides. So angle B is sine inverse. This whole mess, 7 times sine of 70 degrees all over 3. So if you go in and first find the sine inverse, and this sine inverse and this sine can't cancel each other because of this 7/3 in here. Okay. Actually, first I was said do sine 7 times sine of 70, all divided by 3. So this gives me then that B is equal to sine inverse of approximately 2.19. So now if you look and say sine inverse of that answer, it says domain error. So theta isn't between -1 and 1. And so because of that, then we can say there's no triangle exists with this information. So actually, before we go into application, let's go into law of cosines, which is 9.3. So law of cosines we use if we don't know an angle directly across from a side given, and we can't figure that out. We use it when you are given two sides and an angle sandwiched in between, or when you're given all three sides. Okay, so this is law of cosines. And then when we do some application, we use either law of sines or law of cosines. Sometimes we have to use both. But again, so law of cosines you use if you don't have a right triangle. And you know two sides, two different possibilities, two sides and the angle sandwiched in between. Or if you know all three sides. Okay, so law of cosines. It depends on which side you're looking for. So if you know two sides, it depends on which side you're looking for, which of the three equations you're going to use. They're almost all identical. So it starts with a squared. Side of a squared is equal to the sum, so b squared plus c squared. So the sum of the other side squared minus 2bc, and then it's cosine of the angle across from the side of what we're looking for, a squared. So this would be angle A. So if we wanted to look at finding b squared, and so we could take the square root of both sides to figure out what that side is. But b squared, this is equal to the other two sides, that sum squared. So a squared plus c squared minus 2 of those, multiple of those other two sides, ac, cosine of the angle across from the side that we're looking for, b. So my guess, hopefully you could figure out what c squared is. This is equal to the square and summing the other two sides, so that would be b and c. So b squared plus, a squared, b and a, minus 2ab, or it doesn't matter what order you do this in, cosine, and we're looking for side c, so angle c. Basically, if we knew all three sides, we could put those values in here, and then we would be left with cosine of the angle that we're trying to find, and we can isolate it and figure out what that angle is. Okay, so given the following, you're actually given a triangle. This is A, this is 3, bottom is 4, angle on the top is C, angle on the bottom left is B, and we have the angle sandwich in between on the right is 30 degrees. That's a nice one. Okay, so we have two sides. We have an angle sandwiched in between, and we want to determine what side A is, angle B, and angle C. If we know this side across A from 30, then we can use law of sines to figure out the rest, which is probably easier than using law of cosines. And so let's use that formula. So we know then that A squared, the side A squared, is equal to 4 squared plus 3 squared minus 2 times the multiple of the other sides, 4 times 3, cosine of the angle in between that we know, which is 30 degrees. So A squared equals 16, 4 squared is 16, plus 3 squared is 9, minus 2 times 4 is 8, 8 times this 3 is 24, so minus 24. Cosine of 30 degrees, you should know, is root 3 over 2.
Would it have mattered which side we called a, B or C?
No, no, it was just that the triangle was given and they called this B or C, so it really didn't matter. And I would only call this A right here because it said this was, this was side A. And it was crossed. 2 goes in that 24 12 times. So we get A squared is equal to 16 plus 9 is 25 minus 12 root 3. I need to take the square root of both sides. I'm talking about a distance, so it doesn't make sense to have a negative in front of the square root. So here's an example where I could leave it in exact form if you didn't have a calculator. So let's see, so square root, oops. (25) minus 12, another square root, 3 in parentheses and parentheses. So get approximately 2.05. Yeah, they rounded to the hundreds. So angle B and angle C, we could use law of cosines, but it would be easier if we now use law of sines, because now we know the sine 30, and we're trying to find angles, so let's put this in the numerator. So sine of 30 degrees all over the side across from it, which was approximately 2.05, is equal to, doesn't matter which one you look for, B or C. So let's do sine of B, angle B, all over the side across from it, which is 3. So multiply both sides by 3, and then we're going to take the sine inverse of both sides. So sine of B is equal to 3 times sine of 30 degrees all over 2.05. So B is equal to sine inverse of this 3 sine 30 degrees all over 2.05. So sine of 30 is 1/2. So 0.5 times the 3 in front, which was 1.5 divided by 2.05. So this gives us sine inverse about 0.73. Which gives us about 47.03. One more thing we got to find. We got to find angle C. So again, I could use law of sines here, but that's kind of like overkill. We already know 2 of our angles, and so it would be easy to find the third angle by just knowing that they have to sum to 180 degrees. So 180 degrees minus the 30 degrees that we were given, minus the 47.03 degrees given. So 150 minus 47.03. So approximately 102.97 degrees.
I'm trying to like go along with you and put it in on my calculator, and I'm getting a different answer than you.
Okay, make sure is your calculator in degrees mode.
Yeah, so you at first you just did 3 sine 30 divided by 2.05 and then put it into sine negative.
Sine inverse.
Sine
Make
inverse.
sure sine inverse not 1 over that number.
Okay.
Let me just check it again. 3 sine 30 over. Did you get the 0.73?
Yeah, and then whenever I do that to sine inverse, I get like 40, like 48.
Okay, let me try it again. Inverse. Huh. I get 47.029. That's bizarre. And it's not like it's a round, you know. I was thinking maybe it's rounding, but it's not. That wouldn't even round up.
I got the same answer as you.
You did get the 47?
Yes.
Yeah.
Okay, I don't know what's going on. Thank you.
Yeah. So let's, you guys want another example, or you think you're okay? So these you don't, I mean, this was just one example, but these you don't have to worry about 2 triangles existing or no triangle existing if you're given the angle that's sandwiched in between the 2 sides known. Okay, so another example. So solve the following triangle. So this one doesn't give us the triangle itself. I mean, we can always make it if we want, but this says that A is 10. Oh, here's a good one. B is 10 and C is 15. So we're actually given we're given all 3 sides, but we don't know any of the angles. So I don't know, it doesn't matter what we call them, A, B, C, capital A, B, C. So let's try to find one of these angles. How about angle B? So if I was trying to find angle B, okay, so that would mean that I would be using the formula B squared equals A squared plus C squared minus 2AC cosine of angle B. Okay, so plugging this in, across from B was 15. So 15 squared is equal to A squared. So 10 squared plus C squared, 10 squared, minus 2 times A, 10, times C, 10, cosine of angle B. So 15 squared is 225 is equal to 10 squared is
Should that be 10 squared?
B, the angle across from B or side is 15. Is that what you're talking about right here?
Yeah, but doesn't it give us B equals 10?
Oops, you're right. Thank you. So let's change this. I didn't look, I wasn't looking. B is 10. So you're right. So this would have changed where our angles are. You're right, totally right. So I can't just put my angles anywhere, right? So angle B is across from a 10. And angle A is across from a 10. So this would have to be angle C. Can we change that to a C? So this is C squared. This would have been a B squared. This is a C. This would have been a B. We're looking for angle C. Thank you for catching that. So negative 2 times 10 times 10. So 10 times 10 is 100 times 2. So minus 200 cosine of angle C. So if we subtract 100 on both sides, we're trying to isolate this cosine C so we can take the cosine inverse. So if we subtract 100 on both sides, 225 minus 100 is 125 equals negative 200 cosine of C. Divide both sides by negative 200. Well, 25 goes into both of those. 25 goes into the top 5 times. It's negative. And it goes into the bottom 8 times. Equals cosine of C. So we're looking at the cosine inverse of negative 5/8 equals C. So cosine inverse negative 5/8. So get approximately, C is approximately 128. Let me see what they rounded to, if they rounded. They're rounding to the nearest tenths in here. So 128.7 degrees. Okay, so there was actually a reasoning why I chose C. Because if we have angle A is across from the same length, 10, as angle B is the same length, 10, then I know that those angles have to be the same measure. So I can figure that out with some information. If that's the case, if A has to equal B, then we know that angle A is equal to 180 degrees minus C, 128.7 degrees. Let's see. Can we do that? Or no, here we know. This is what we know. If I sum those two angles together, A plus B has to be the sum of the measure left. So A plus B would have to equal 180 minus 128.6. 180 minus this answer. So that gives me approximately 51.3. But A is equal to B. So that tells me that A plus A is equal to 51.3 degrees. So that tells me 2A equals 51.3 degrees. Divide by 2, we get A is equal to about 26.7 degrees. Which is the same thing as angle B. If you didn't know that reasoning like I just kind of did, then we would have used law of sines. It would have been kind of overkill to use a law of cosines again. And so let's just show it real quick. So if I was trying to find sine of A, angle A, so sine of A all over 10 is equal to sine of B, or not sine of B, which one? Sine of C. C we found to be 128.7 degrees all over the side across from angle C, which was 15. So if I multiply both sides by 10, I get sine A equals 10 times this sine, 128.7, all over 15. Things simplify a little bit. Really don't need to worry about it, but 5 goes into both of those, goes into the top 2 times and the bottom 3 times. So A is equal to the sine inverse of that. Of 2 sine of 128.7 degrees. Now divide that by 3. So 2 sine 128.7, take that answer, divide it by 3. That should give you approximately 0.52. So when you take the sine inverse of that answer, you get approximately, oops, I get something different. 31.35. Let me just make sure I plugged everything in right. Yeah, I got 31.35. You got 25.67 back over here. Did you guys get all of the 128.7? That's C. Under 28.7. Maybe my reasoning is wrong. I would think that though that since the angles are the same, the sides are the same, the angles would have to be the same.
Is the professor?
Mm-hmm.
Is the A equals sine inverse 25 inches, and then in the parenthesis is that 128.77?
No, that should just be 120. That was a parentheses here. This is a 128.7 with a parentheses just around that sign piece. Did I do something wrong? So, because this we would have multiplied by 10 on both sides. And then 10 and 15, they both reduce to 2/3. Okay, well, let's stop here. I'll see if my husband can see the error while we're on a break. But you got some examples, and I'll go over that when we come back. Let me just pause the video. Okay, so during break, I figured out where my error was here at this point when we, at the beginning, where we were squaring each side that we knew, 10 squared plus 10 squared. Well, that's 100 plus 100, which should have been 200 here. And so it had to do back with this. We had the right idea of how we were going about this, and your angle should have been the same for A and B, like I was saying. For time-wise, I am not going to go and fix that right now because I want us to get to grading the test that you took yesterday. So first of all, if you have a initial on the upper right-hand corner, good job. You read through the directions and you got an extra credit point. So that last piece of the direction says initial the upper right-hand corner of your exam, verifying you read these directions for an extra credit point.
If we did it as PDF form, though, we wouldn't be able to initial it, right?
Excuse me?
If we did it as PDF form, we wouldn't be able to initial it.
You should have been taking the test not in a PDF. You should have been taking the test on a piece of paper and then uploading it. Yeah, so how would have you done that? How would have you taken the test if you couldn't write on it on a PDF? I'm a little confused on that. Okay, so if you initialed that, we might need to talk later. So if you initialed it, you get a point. I'm going to rotate it. So the following A through C are worth 3 points each. Sine inverse of root 2/2. I notice that this is positive, that my domain or my range for a sine inverse has to be between negative pi halves and pi halves. This tells me that this is in quadrant, theta is in quadrant 2. Sorry, not quadrant 2, quadrant 1, and that this theta is equal to pi force. Here, cosine inverse, oops, and so that was worth 3 points. So give yourself 3 points if you got that right. Give yourself, if you had some information but had the kind of wrong idea, you maybe give yourself 2 out of 3. So usually what I do here is I'll do +3. Or if I have some point where they're not getting all the credit, then I'll do how many points they get out of 3 here. So the next one, here I can tell cosine inverse is negative root 3/2. I have a negative value. I know that my my range has to be between negative or 0 and pi. So theta has to be between 0 and pi for cosine. I notice that this is negative. So I notice that theta is going to then be in quadrant 2. So my reference angle, though, that gives me back positive root 3 over 2 for cosine, that is 30 degrees. It didn't say anything about radians in here, so you could have done 30 degrees or you could have done pi 6. And so depending on that reference angle, theta getting us into quadrant 2, well, 180 minus 30, so theta is either, your answer could have been either 150 degrees or pi minus pi 6. So 6 pi 6 minus 1 pi 6 is a 5 pi 6. Same idea for sine inverse of negative 1/2. So this you got right, give yourself 3 points. If you were off a little bit, 2 out of 3. If you didn't have any idea, 0 out of 3. A little bit of an idea, maybe 1 out of 3. So here, again, sine inverse, I have to be between negative pi halves and pi halves. But this is negative, so I'm in quadrant 4. My reference angle, if I'm thinking about sine, when sine of what angle gives me positive 1/2, that's 30 degrees or pi 6. But I'm in quadrant 4, so I have to, and it's in the form of minus, so the degree is counterclockwise. So pi 6 or 30 degrees is the reference angle, but theta would have been equal to either 5 pi 6, I'm sorry, is equal to negative pi 6 or negative 30 degrees. Either answer would have worked. And so that one was also worth 3 points.
Would 330 degrees have worked?
So if it's 330 degrees, give it 2.5 out of 3 points. Just because of the sine inverse piece being here. If it had been like sine theta equals negative 1/2, then when we were taking the sine inverse of both sides, you could have written theta as that 330. But since it started like this, you want to give it in between the negative pi halves and pi halves, or negative 90 and 90. So this one you had to be careful. So I only looked at 2 exams. Tan inverse of tan, normally that undoes each other, but we have to be careful if this angle is not in our I always get a confused range domain. It's when it's opposite. So 5 pi 4 is not in the range. And so we have to first rewrite this. And so you could have done some side work on here. So 5 pi 4, so if we rotated 5 pi 4, well, this is 1 pi plus another pi is 5 pi 4. And so I noticed that tangent is in the 3rd quadrant, meaning it's positive. And tangent of 5 pi 4 is 1. So this, we would have tangent inverse of 1. And so now if we look at tangent inverse of 1, well, this has to be between negative pi halves and pi halves. Can't be pi halves or pi halves because it's undefined there. And theta, this is positive, so I know that I'm in the 1st quadrant. And so the value that would give me this back would be pi 4. Tangent of pi 4 is 1. So 3 out of 4 points if you had done just 5 pi fourths. And then give yourself 4 points. These last 3 are worth 4 points. If you got it right.
So I had gotten the pi fourths, but I circled the 1. Does that matter?
No. Unless you were thinking that was your answer. But if you accidentally were circled that. So sine inverse of cosine of negative 7 pi 6. So I would first look at where's negative 7 pi 6, and I would evaluate cosine there. And so if we go negative 7 pi 6, well, if I go pi, that's 6 pi 6, and I have to go clockwise because it's negative. And then 7 pi 6, so another pi 6 would get me 7 pi 6. So this is negative 7 pi 6. My reference angle then is pi 6. And cosine in the second quadrant is negative. So this would give me sine inverse of negative, and cosine of pi 6, cosine of 30 degrees is root 3 over 2. So now when we evaluate this, our range is only between, for sine inverse, between negative pi halves and pi halves. So this tells me that theta in this case is contained in quadrant 4. I know that sine inverse, or sine of inverse of positive root 3 over 2, that's at 60 degrees. This was in terms of radians, so my answer really should be in terms of radians. And 60 degrees is pi thirds, but it's negative, and I need to be in quadrant 4. So our answer here is negative pi thirds. So again, that's worth 4 points. Give yourself partial credit if you didn't get it based off of your knowledge. 7 pi 6, it's almost the same, but this is 7 pi 6, positive 7 pi 6. So going the opposite direction, counterclockwise, that would get us down into the third quadrant. Our reference angle is the same, it's pi 6, but it's in the third quadrant. And this time we're looking at sine of 7 pi 6. Well, sine of pi 6, sine of 30 degrees is 1/2. But we're in the third quadrant, sine is negative. So this is cosine inverse of negative 1/2. So cosine inverse, we're between 0 and pi. Cosine inverse, cosine is negative in quadrant 2. I think about my reference angle, that would give me back positive 1/2, which I know is 60 degrees. Did I do that wrong? Okay, 60 degrees. And so cosine inverse of 60 degrees, pi thirds is 60 degrees, but I need to be in this quadrant over here. So theta has to be, in this case, contained in quadrant 2. Our reference angle would be pi thirds. And so pi minus pi thirds to get me up in here for cosine inverse, that is going to be 2 pi thirds. Or just 2 pi thirds. Really, this is not data. Okay, so that was worth 4 points. Okay, so there was 2 different ways that you could have approached number 2, part A. You could have written that as a half angle identity, or you could have written that and using the half angle formula, or you could have figured out 2 angles that sum, or the difference is 15 degrees, that you knew what the angle was. And so it depends on what way you did it. Hours at a time. I'm gonna have to pick up speed. So sine of 15 degrees. I wrote this first as a half angle. So this is going to be sine of 30 degrees over 2. As a half angle, well, sine 15 degrees, quadrant 1 is positive. So this has a positive in front of the square root. And then the square root of 1 minus sine of 30 degrees. I'm sorry, cosine of 30 degrees. All over 2. So this is equal to the square root 1 minus cosine of 30 degrees, that's the root 3 over 2. And then we actually have this in our denominator, the 2. Simplify, get rid of the complex fraction. And so here we would get, distributing, we get root 2 minus root 3. All underneath that radical, the 2 here cancels, and 2 times 2 is 4. Square root of 4 is 2. Okay, so if you did the half angle identity and you showed your work, then give yourself full credit. This one was worth 4 points. If you did this and you just jumped from here to the answer, I'm not going to give you credit, maybe 1 out of 4 points. And then you could have done it as a sign or a sum or difference. Notice that 15 degrees, that's the same thing as 45 minus 30. So we could have written this as 45 minus 30. Sine difference is sine, cosine, same sign, sine, cosine. So sine of the first, 45, cosine of the second, 30. Minus sine of the second, 30, cosine of the first, 45. Sine of 45 degrees, that one is the root 2 over 2. Cosine of 30 degrees, that's root 3 over 2. Minus sine of 30 degrees is 1/2. Cosine of 45 degrees is root 2 over 2. So we can simplify a little further by combining this as one fraction. We have root 2 times root 3, that's root 6 all over 4. Negative 1 times root 2, so minus root 2 all over 4, so this is one fraction. Okay, so if you decided to use the sum or a difference of 2 angles, you should have gotten something similar to that.
Excuse me, Professor.
Yeah.
If we forgot to multiply to get 4, and like if we put 2 instead of 4, how many points would be deducted?
If you got everything else right, I would notice that you had that there. You have probably, did you have the 2 times the 2 down here? You just forgot at the very end, the 4.
Yeah, I just forgot.
Give yourself 3.5 points out of 4 points. This one we don't know how a sine of 70 or cosine of 40 or vice versa. But if you look at it, sine, cosine, cosine, sine, sine, cosine, sine, cosine, just kind of what we just did, breaking that down. And so notice that this is actually going the opposite direction. And this is sine. And this was the difference of angles because it was the same sign. So 70 degrees minus 40 degrees. If we do that, that gives us sine of, well, 70 minus 40 is 30 degrees. 30 degrees, sine of 30 degrees is 1/2. So that was worth 4 points.
If like, for example, if I just put sine 30, how much?
You should have evaluated it. Give yourself 2.5 out of 4 points. It depends on how you would have rewritten the pi 8s in order to manipulate it. I did it as multiplying this by 2/2 to make this a half angle. Just multiplying it by a fancy kind of 1. And when I did this, I get cosine. Well, this is really 2 pi all over 8 divided by 2. So if I flip that 2 up, it would cancel, giving me back that pi 8. But notice, let's rewrite this a little differently. Let's cancel this. Come on. Cancels and making this a 4. So we now have this cosine of pi 4s over 2. And so we can use our half angle. Pi 8s, that is in quadrant 1. So our half angle would have a positive in front of the square root. Cosine is 1 plus cosine of what you were taking the half angle of, which is pi 4s in our case, all over 2. Sorry, things are not. Okay, so this is equal to positive square root. Come on. 1 plus cosine of pi 4s, that's root 2 over 2, all divided by 2. So got to kind of manipulate this. Let's multiply this by 2 over 2. Distribute. So this gives us square root 2 plus, the 2 cancels here, root 2, all over 2 times 2 is 4, but the square root of our denominator 4 just leaves us with a 2. Okay, so that one was worth 4 points. Tangent of 75 degrees, it really depends on which way you wrote it. I rewrote that as a sum of 2 angles, I know, 30 degrees and 40 degrees. 45 degrees. So you have the formula, and tangent sum of angles is tangent of the first, so 30 degrees, plus tangent of the second, 45 degrees, all over 1 opposite sign minus tan of the first, 30 degrees, times tan of the second, 45 degrees. Tangent of 30, that one is the root 3 over 3, plus tangent of 45, that is 1, all over 1 minus tangent of 30 degrees, again, is root 3 over 3, and tangent of 45 degrees is 1. You want to clean this up so that it doesn't have a radical in the denominator or complex fraction. We can look at the fractions within the fractions, see that your denominator is 3, so we can clear that by multiplying by a fancy one of 3 over 3. And so when we distribute that, we get root 3 plus 3 all over 3 minus root 3. And then let's rationalize the denominator. So we have to multiply this by 3 plus root 3. 3 plus root 3. So if you FOILed this out, this would have given us 3 root 3 plus a 3 root 3 is a 6 root 3. This would have given us a 9, and this would have given us plus a 3, so that would have been plus a 12. All over, this is a difference of squares, so 3 squared minus, so 9 minus root 3 squared, 3. You can factor 6 out of the top, which gives me root 3 plus 2, all over 6. That cancels. So our final answer is root 3 plus 2.
So for this one, if the process was right, but then I just got lost in like that very end algebra part, how many points did I get?
This one was worth 4 points. So depending on how lost you did, I'd be between 3 and 3.5 points. Here, part E and F are worth, what is it? Did I say? E through G are worth 5 points. Wondering. Okay, so cosine of 1/2 sine inverse of 3/5. This is where you're going to need to make a triangle. We don't know what sine inverse of 3/5 is. It might be easier, you guys, if I actually just write this out instead of using this document. And I have the test right in front of me, so let me just do that. So right now, what are we? We're on okay, so we have cosine of 1/2 sine inverse of 3/5. We don't know sine inverse of 3/5. We don't know what angle would give us that back. And so this is where if we let theta equal sine inverse of 3/5, we take sine of both sides. So sine theta then is equal to 3/5. We make our triangle. If this was theta, sine is opposite 3 all over hypotenuse 5. This right here, using the Pythagorean theorem, the square root of the hypotenuse squared minus the leg squared, 3 squared. This is 25 minus 9 is square root of 16, which is 4. So now let's go back in there and rewrite this. This is the same thing then as cosine of 1/2 times, well, we let sine alpha or sine inverse of 3/5 be theta. If we look at this, this is the same thing as the square root using my half angle. This is a cosine, so 1 plus cosine of theta all over 2. Well, we had the triangle up there, so we could figure out what cosine of theta is. So cosine is adjacent, which is 4, all over the hypotenuse, which is 5, all over 2. So I don't like complex fractions, and so I would multiply by a fancy one to get rid of that complex fraction, 5 over 5. And so this is equal to the square root of 5 times 1 is 5 plus 4 all over 2 times 5 is 10. So this is the square root of 9 in the numerator, which is just 3, all over the square root of the denominator, 10. Don't like radicals in the denominator, so quickly rationalize it, multiply both top and bottom by square root of 10, so we get 3 root 10 all over 10. So that was 5 points. Similar idea for the F to F. Here we have sine of 2 cosine inverse of -3/5. Again, this is not a cosine inverse. I don't know cosine of what angle gives me back -3/5. So this is where I would create my triangle. I can tell because this is a negative that my theta value here is in quadrant 2, because cosine inverse is between 0 and pi. And so this has to be between pi, or pi halves and pi. So I would let theta equal my cosine inverse of -3/5. I would take cosine of both sides. So cosine theta is equal to -3/5. I would make my triangle opposite over, or sorry, cosine is adjacent over hypotenuse. So this is 3, 5. These actually are the same, not exactly the same, but it was 5 was the hypotenuse before, and 3 was the side before too. So 5 squared is 25, minus 3 squared is 9. 25 minus 9 is 16. This is equal to 4. So let's rewrite it. This is really sine of 2, but this is cosine inverse of this -3/5 we called theta. So let's just replace it with theta. Use your formula for sine of 2 theta. This is equivalent to 2 sine theta cosine theta. So this is 2, well, sine theta, let's use our triangle, is opposite over hypotenuse, so 4/5. And cosine theta, adjacent over hypotenuse, which is 3/5. Be careful though. Theta is in quadrant 2. And we already knew this was negative. And sine in quadrant 2 is positive. And so just multiply across. We got 2 times 4 is 8 times -3 is -24, all over 5 times 5, which is 25. So we only have 8 minutes, so I'm just gonna, I don't think we're gonna get through this, but we're gonna start flying on this. So cosine of tan inverse of -1 minus sine inverse of -4/5. So I would look at this. I actually know what tangent inverse of -1 is. So we could actually simplify that. Well, tan inverse of +1, tan of pi force gives us +1, but this has to be, it's negative, so it has to be in quadrant 4. So this is going to be negative pi force. So far we have cosine minus, well, we can't figure out, or I don't know what sine inverse of 4/5 is, so let's call this theta. So we're going to let theta equal the sine inverse of -4/5. Taking the sine of both sides, sine theta is equal to -4/5. Theta is contained in quadrant 4 to be negative. Make your triangle. So sine is opposite 4, hypotenuse 5. This side ends up being 3 when you use the Pythagorean theorem. If you look at this, we could factor out a negative. So this would be cosine plot of -1. So that would actually be pi force plus pi. I'm sorry, pi force plus theta. Cosine of a negative is the same thing as cosine of the positive because it's even. Or you could have done that later. So this is cosine of pi force plus theta. So sum of two angles for cosine is cosine, cosine, opposite sine, sine, sine. So this is cosine of pi force, cosine of theta, minus sine of pi force, sine of theta. And so now evaluate this. So cosine of pi force, we have √2/2, cosine of theta, but cosine of theta, we can use our triangle. I'll come back to that. Minus sine of pi force is √2/2. And again, we can evaluate sine of theta with our triangle. And so cosine of theta adjacent over hypotenuse, which is 3/5. You have to determine positive or negative. Cosine is positive in quadrant 4. And then sine theta, we have is, well, we were actually given that up here, -4/5. So simplifying, we have 3√2/10 minus, well, minus and a minus, so plus 4√2/10. These are like terms, and so this gives me 3√2 all over 10. So that one was worth 5 points.
I got 7√2/10.
Oops, you're right. I'm getting sidetracked. Are you guys okay with hearing me? It came up that the audio could have been off. And sometimes I'm looking up and the screen is kind of frozen.
Yeah, we can hear you.
Okay, thank you. Okay, so the other one's number 3 was solving equations, and it told us that we're only finding solutions between 0 and 2 pi. And so 3a was 4 cosine squared of theta minus 3 equals 0. So looking at this, I noticed that I can isolate cosine squared theta and then figure out what cosine theta is. So let's isolate cosine squared theta. You would add 3 to both sides and divide by 4. You get cosine squared theta is equal to 3/4. Taking the square root of both sides, we get cosine theta is equal to plus or minus the square root of 3/4. So cosine theta, we're looking at when is this positive √3 all over 2, and when is cosine theta equal to negative √3/2. Well, theta, our reference angle in quadrant 1, that is 30 degrees, which is pi 6. So theta is equal to pi 6. It's also positive in quadrant 4. So 2 pi minus pi 6 is 12 pi 6 minus 1 pi 6 is 11 pi 6. For negative, that would be quadrant 2 and quadrant 3 for cosine. So pi 6, pi minus pi 6, that's 6 pi 6 minus 1 pi 6 is 5 pi 6. Or pi plus pi 6, 6 pi 6 plus 1 pi 6 is 7 pi 6. So here's the measures or the values between 0 and 2 pi for that. That was worth 5 points. Sine of 2 theta.
That's it.
Mm-hmm.
But I only had pi over 6 and 11 pi over 6. Would I give myself 2.5?
So you got it all except that you didn't get the negative part because maybe when you took the square root of both sides, you forgot to put the minus. Is that what happened?
Yeah.
If that's what happened, give yourself 3.5 out of 5 points. Because you really did have the right idea. It was just that you missed that one piece in here with taking the square root of both sides, putting that minus.
Yeah. Okay.
Here, I would go in here and I would think about when is sine of what? Some single angle, or like sine, when is sine of A equal to a positive 1? Ignore this negative 1 for a second. Just think of it as positive 1. Well, I know sine is positive 1 at pi halves. And it's negative 1 at 3 pi halves. So this is sine of A equals negative 1 when A is equal to 3 pi halves. There's no sine inverse in here, so I don't have to look at it as negative pi halves. Okay, well, let's think of this as A. So we actually really have to look at when is 2 theta minus pi halves equal to 3 pi halves. The problem is that things can get affected because of this. So I need to put in here the other values, this 2 pi k. So I want to solve for theta. So if I add pi halves to both sides, so 2 theta equals, well, pi halves plus a 3 pi halves, that's a 4 pi halves plus 2 pi k. That actually reduces. So 2 pi plus 2 pi k, 2 theta equals that. So if I multiply everything through, I could divide by 2, or multiply everything through by a half. That gives me theta then is equal to 1/2 times 2 pi is just pi, plus 1/2 times 2 pi k is just pi k. So we need to look at values of k. So if k was equal to 0, that would tell me then that theta could be pi. If I let k equal 1, that would give me pi plus k times 1 is pi plus pi. That's 2 pi, but our thing said between 0 and including 0, but not including 2 pi. So I noticed that this is when theta then is equal to 2 pi. This is not in that set, but if you let k equal -1, pi plus a negative pi is 0. So I actually have to also include 0 as part of that set. And so there's 2 solutions theta can be to make that sign of 2 theta minus pi halves equal to -1.
So what if you didn't add the 0? Because I got pi, but I just didn't add the 0.
Give yourself 4 or 4.5 points out of 5.
Okay.
I used the double sine equation and got the right answer somehow. Was there a way to do that, or was that just chance?
I think that might have been just chance. I'm thinking that, I could have done this where I could have rewritten this as sine, sine, cosine, because I see a difference of angles and kind of manipulated it. But this is equal to -1, so I would have some problems.
And what if I followed, like, had the same idea, I just didn't get the right answer?
So if you have the general right idea and there was, some simple error that didn't get you the right answer, then give yourself most of the points, like 3.5 or 4.5 out of the 5 points. If you're really missing a concept in there, then, 2.5 points. If you have some things that you're missing, a couple of different things, maybe, but you have a general idea, maybe 3 out of 5 points. So I know I kind of kept you guys already over. I don't mind staying and doing a little more, or even I have to teach at 1. But I probably can hammer through this and finish it. And those of you who can't stay, you can always come and watch the video later. Or we can try to pick up on this tomorrow on the second half. What would
I
you
have to
guys
go to
prefer?
work, but I don't mind watching the video later, so you guys can
Okay.
do it.
Okay, so let's continue. Let me just continue on and go through this. So C, that would have been sine squared theta minus cosine squared theta is equal to 1 plus cosine theta. So when solving equations, a lot of times it's helpful to have, if you can't factor it and set it equal to 0, it's helpful to have everything in terms of all the same trig function. And so I notice I have cosine squared and a cosine theta. So I also notice sine squared could be rewritten in terms of cosine squared using the Pythagorean identity. Cosine squared plus sine squared equals 1. So if I subtract sine squared on both sides, I know this is the same thing as cosine squared. I'm sorry, 1 minus cosine squared theta. So I'm just going to replace sine theta with a 1 minus cosine squared theta, and then rewrite the rest of the equation down, which is minus cosine squared theta equals 1 plus cosine theta. So notice I can combine my terms on the left-hand side. Now we have a negative cosine squared theta minus a cosine squared theta. So that's 2 of them. So 1 minus 2 cosine squared theta is equal to 1 plus cosine theta. So looking at what type of an equation it is, it's quadratic. And so I want to get everything to one side of the equation and set it equal to 0, and hopefully we can factor it. And so if we add 2 cosine squared theta on both sides, and let's subtract 1 on both sides. Well, that's nice. Our 1's cancel. And so all we're left with is 2 cosine squared theta plus cosine theta is equal to 0. So since our constant is gone and our 2 terms have a cosine in it, we can factor out one of the cosines. So pulling out a single cosine theta from both of those terms, we're left with 2 cosine theta plus 1 equals 0. So you're looking at when is cosine theta equals 0 and when is 2 cosine theta plus 1 equals 0. Well, cosine is 0 at pi halves and 3 pi halves. And if I solve for cosine here and I subtract 1 and divide by 2, I am looking at when is cosine theta equal to -1/2. Well, when theta first quadrant is 1/2 at 60 degrees. But negative first quadrant and second quadrant and third quadrant. So 60 degrees, which is pi thirds. So to get into the second quadrant, that's 2 pi thirds. get into the first quadrant, I'm sorry, third quadrant, that is 4 pi thirds. So that was C, again, 5 points. D, we have 4 all times 1 plus sine theta equals cosine squared theta. So again, I noticed that my equation it has multiple trig functions in it. It's not going to help me. I can factor it and set it equal to 0. So I want to get this all in terms of sine or cosine. Since we have cosine squared, we can rewrite that in terms of sine squared. So rewriting sine or cosine squared in terms of sine squared, well, cosine squared is 1 minus sine squared theta. At the same time, let's distribute our 4. So let's rewrite that. So distributing the 4, we have 4 times 1 is 4 plus 4 sine theta is equal to 1 minus sine squared theta. Let's get everything to one side of the equal sign because it's a quadratic. So let's add sine squared to both sides. So there's sine squared theta plus 4 sine theta. And I'm also going to subtract 1 on both sides. So I have a 4 minus 1 is, so plus 3. This equals 0. There are 2 numbers that multiply to give you positive 3 and add to give you 4. So this factors as sine theta plus 3 and sine theta plus 1. So we're looking at when is sine theta equal to 3? Oops, sorry. Sine theta plus 3 equals to 0. And when is sine theta plus 1 equal to 0? So we're looking at when is sine theta equal to negative 3? Well, there's no value of theta that gives you a number smaller than negative 1 or bigger than 1. And so this is not in the domain. This is not possible. Solving for sine theta for the second equation, though, we're looking at when is sine theta equal to negative 1. There's only one value where it's equal to negative 1 between 0 and 2 pi, and that is at 3 pi halves. So part D is 3 pi halves. These actually came out pretty nicely. So prove the following. Here you had sine squared theta all times 1 plus cotangent squared theta. We want to show that this is equal to 1. So we're only working with one side here. So let's rewrite this cotangent in terms of sine and cosine. So working with the left, sine squared theta all times 1 plus, well, cotangent squared theta, cotangent's the same thing as cosine over sine. So this would be cosine squared theta over sine squared theta. Let's distribute your sine squared theta. So if we do that, we get sine squared theta times 1 is sine squared theta plus sine squared theta times cosine squared over sine squared. Sine squares cancel, leaving you with cosine squared theta. But this is our Pythagorean identity, which is just 1.
For that one, I put that the 1 plus cotangent squared also could just be cosecant squared, which is 1 over sine squared. Does that work?
Yep. So noticing that 1 plus cotangent squared theta was one of those Pythagorean identities, you can do that. That would have worked.
Professor, so I got 1, but I got it another way.
Did you just work on one side of the equation?
Yeah, but for 1 plus cotangent squared theta, I changed it to cosecant squared theta.
Oh yeah, that was just what, I don't remember who just said that. I wasn't looking when you said
I'm
it.
sorry.
No, you're good. But basically here, so another way to do this is just like you said. I wouldn't have noticed that right away without looking at it first. I know that this is equal to 1, right? I knew that this has a cotangent squared in here. I know cosine over sine is cotangent, so I would have divided everything through here by sine squared theta. And then you would have noticed that this is 1 plus cosine squared theta over sine squared theta is cotangent squared theta. And that's where you guys got that this was cosecant squared theta. And so basically we could say, well, let's just rewrite this 1 plus cotangent squared theta as cosecant squared theta times the sine squared theta out front. And then you would have rewritten cosecant squared theta as 1 over sine squared theta. Those cancel, giving you 1. So that does work too. So there's multiple, ways that you can approach some of these showing, and it depends on which identities you chose to use or how to do it. So yeah, give yourself full credit. Good job.
What were the points again? Was that 4?
That one, I believe, was 5 points. Is that right? I don't have this test. This was what I'm looking at right now is my solutions, which I took the test before you guys took it just to make sure it looked okay. So I didn't have the points figured out totally at that point. So cosine of alpha plus beta all over cosine alpha sine beta. We want to show that this is equal to cotangent beta minus tan alpha. So choose a side to work on. I chose the left. You could have chosen the right. I noticed that cosine alpha plus beta, I can change that using the sum of angles for cosine. Cosine again is cosine, cosine, sine, sine, opposite sign in between. So this is cosine alpha, cosine beta, opposite sign minus sine alpha, sine beta, all over cosine alpha, cosine beta. We can rewrite this as 2 separate fractions. So cosine alpha, cosine beta, all over cosine alpha, cosine beta. Did I write that? Oops, I copied this down wrong. This was sine beta down on the bottom. Knew something was wrong because I wasn't getting where I wanted. Okay, so minus sine alpha, sine beta over our denominator, cosine alpha, sine beta. So notice things cancel out. So with our first grouping, our first fraction, the cosine alphas cancel. And you're just left with cosine beta over sine beta, which is cotangent beta. Minus, over here, our sine betas cancel, and you're left with sine alpha over cosine alpha. Sine over cosine is tangent, so this is tangent alpha. It's what we wanted to show up here, so we're done. Okay, so I ended up changing this next problem, number 5. This was only one I ended up changing on the exam. I believe that the new equation that I put and you guys had was -2 sine of pi times x.
It wasn't -2, it was just 2.
Oh, it's just 2, okay. So 2 sine pi x and then -1. Oops, I gotta change the one there. Okay, so it asks what the amplitude is. The amplitude is given by the value or coefficient in front of our trig function, only for sine or cosine, and the absolute value of that. So the amplitude is just...
Mrs. Knopflinger, I believe it was actually -2, not +2.
That's what...
I have -2 as well.
Okay. So the one who said +2, you might have just copied it down a little bit wrong, and so give yourself most of that points because it was just off because of how you copied it. Like maybe just knock off a half a point if everything else is right according to your equation. So amplitude is the absolute value of -2 for this, which is 2. Our period we can find by looking at our argument and sandwiching it in between 0 and 2 pi, because that's what our normal period is for sine. Divide both sides by pi, or all 3 sides by pi. We get 0 is less than x is less than 2. So our period has a length of 2, between 0 and 2. And so if I split this up, so we have 0, we have a halfway mark, which would be 1, and then a 3/4 mark, and then 2. So halfway between 0 and 1 is a half, halfway between 1 and 2 is 3/2, or 1.5, or 1 1/2. Now you got to figure out, normally without this -1 in here, our max would be at a 2 and our min would be at a -2 because of our amplitude. This -1 is shifting everything down 1 unit. And so instead, it's like our midway line, which before was our x-axis, is now shifted down 1 unit. And so it's like at y equals -1. And so instead of our min being at -2, since it's shifted down 1 unit, our min is now at -3. Our max before was at 2, but we shifted it down 1 unit, so now it's at 1. And so part C was asking what the range is. Your range are your y values. We're going to hit -3, so include it, and we're going to hit 1. So you could have written it as with the brackets -3, 1, or you could have written it as -3 is less than or equal to y is less than or equal to 1 is another way. Sine function normally starts at the origin. So we're going to start here at our midway line. Normally it goes up to the max, but that minus is a reflection, and so it's going to go down first. So at the halfway or quarter point, which is 1/2, we're going to hit the min. At 1, we're going to come back, hit the midway line. 3/2, hit our max. And at 2, come back down and hit the midway line. And so we get 1 cycle right there of our graph. So that was, I think, different types of points on there. Maybe 2, 2, 3. I don't remember what I did it offhand. One more. So an object moves in a simple harmonic function described as the following. D is equal to negative cosine of pi times t, where d is measured in inches and t is measured in seconds. So find the maximum displacement. Well, this cosine, our amplitude, is 1. And so the max that we can get going from the equilibrium up is 1, and then down would be -1. So the maximum displacement is 1 inch, because this is distances in terms of inches. find the frequency, frequency is equal to omega over 2 pi. Well, looking at our equation, omega is pi. So we have pi over 2 pi, which is equal to 1/2. So it takes half a second to get through frequency. It's occurring every 1/2 second. So find the time for one oscillation. I would think that's the same thing as the frequency. Time of one oscillation. This is the period, which is 2 pi all over omega. So this is 2 pi all over omega, which is pi, which is equal to 2. Okay. So I believe the first one was 2 points, B was 3 points, and C was 3 points. So normally what I do is I go through and I sum up each problem. I know, like, for example, 6 was worth, if it was worth 8 points, I would put the score over 8. And then I would sum up all my scores and my numerators, even though this is really not like math, because we don't have a common denominator. Basically, I just score up all my numerators, and that would be the score out of, in this case, this test was out of 100 points. And so on the upper right hand,
what was it for 6 again? It was 2, 3, 3?
I believe so.
Okay.
But it's on, you can pull it up too. Let's see. I have it on my test. That's college algebra. Sorry. I don't have the test on me right now, offhand. I don't have it right offhand, but it's on the test. I'm going to actually let you guys go so that I have like a little break before I have to teach in 10 minutes. Yeah, so look online. You can pull up the test again on the Canvas page. Just click on the test and look at the bottom, and it will tell you on the page next to the question how much each piece is worth. Thank you. So it was 233. So I will create an account in Canvas for you to send this to me. It won't be done until I finish my next class. So it will probably be up around 5 today. So, and I will give you guys some time to get it in because not everybody stayed and watched the video. So I'll give you a few days to look at that and get it in. Other questions?
So do we just send our score to you?
No, I want to see the grade, how you graded it. So send me your graded test. So you're going to upload your exam again, but in the graded versions.
Okay.
But I will put that in the directions, and you'll see the assignment later today. Okay, you guys have a wonderful evening, and I will see you tomorrow.
You too. Thank you, Professor.
You're welcome.
Right.
Bye.
Professor.